Okay, students, we're now going to talk about magnetism. What is that? Now, magnets actually were known since ancient time and what was called lodestone, which were very, very important for the navigation of ships because a lodestone would always point to the north. It was a magnet. And over time, as we will see, the relationship, very important relationship between magnetism and the electrical force became known. In the previous lecture, we saw that charges can be considered to be monopoles, or point charges that sort of radiate out in all directions. A magnet is different in a sense that a magnet has two poles, and we've always traditionally called them north and south, the north pole and the south pole. And you've probably heard from some science class long ago that if you take a bar magnet and you cut it in half or saw it in half, the two pieces will still have a north pole and a south pole. And you also know that the two north poles or the two south poles, if you try to push them together, they will repel, but the north and the south pole will attract each other. Now this drawing illustrates some basic similarities, however. With charges, we said that if we had a positive and negative charge and we bring them close together, there will be attractive field lines, as sort of illustrated here. Now we can't see these field lines, but they're there, and they are what causes attraction between the positive and negative charge. With a magnet, and let's think about a bar magnet, there are also these field lines that radiate between the north and the south pole, as shown here. Very, very similar field lines. Now, while we can't easily see that for electrical forces, you've probably seen demonstrations of this. If you have a bar magnet and you have some iron filings, that the bar magnet will actually reorient the iron filings and create these field lines, or you'll be able to see these field lines that are created by the magnet. Now, there was a very interesting accidental discovery by a Danish professor named Hans Christian Ørsted. This is kind of like the way science is done sometimes, just serendipitous findings. Ørsted was turning on and off an electrical circuit, and he noticed that a compass, one of these lodestone permanent magnets or a compass, that the needle of the compass would jiggle. So that an electrical circuit is causing the compass, the magnet of the compass, to move. That is, there must be some relationship between electricity and magnetism. Gadzooks, Ørsted said, which of course is Danish for by golly. This led him to discover that a magnetic field can be created by the motion of electric charges, because the electric circuit is a movement of charges. Movement of charges can influence a magnetic field and can actually create a magnetic field. This is a phenomenon called electromagnetic induction. A moving charge, a moving electric charge, can produce a magnetic field, and conversely, a moving magnet can produce an electric field in a conductor. That is, it can produce current. Sounds like that might be important. That is, there's a fundamental and very important relationship between electricity and magnetism. And one way to illustrate that relationship is shown in the bottom drawing, which shows an electrical wire and someone attempting to grab the electrical wire to illustrate what is called the right-hand rule, that if you grab an electrical wire, and if the electricity flows in the direction as shown through this wire, there will be a magnetic field that is produced perpendicular to the wire in the direction of your right hand, that is curved in that particular direction. Magnetic field extends outside of the wire perpendicular to the direction of flow of electric current. Wow. A moving charge produces a magnetic field that can even extend beyond the wire. And we will see also later that a moving magnet can produce electric current. You've also probably heard of electromagnets. That is, if you take an electric wire and you coil it up as shown in the left, pass electricity through this electric coil, it produces a magnetic field very similar, just like that, for a permanent magnet. I show an electromagnet on the left and a permanent magnet on the right. And you see these magnetic field lines. It also turns out that if you take this wire loops and you wrap it around an iron core, it becomes an even stronger electromagnet, what we call a solenoid. So this is what an electromagnet is and how it's similar to a permanent magnet. Now this slide, very wordy, but it has a lot of information. Now there were several scientists who contributed to the development of our understanding of electromagnetics. Franklin, Coulomb, Oersted, Galvani, Faraday, Edison, Maxwell, probably we can name some more. The phenomena of electromagnetics can be summarized in terms of what is called Maxwell's equations, of which there are four. 1. Like charges repel and unlike charges attract. That can also be called Coulomb's law. 2. There are no magnetic monopoles. That is, a magnet occurs as both north and south, or occurs as a dipole, whereas charges can be monopoles, single point charges, either plus or minus. A magnet will always have a north and a south pole. 3. Magnetic phenomena can be produced by electrical effects. That is, a moving electric charge can produce a magnetic field. And 4, which is the converse, electrical phenomena can be produced by magnetic effects. Now these latter two phenomena are the basis for our generation of electricity. We will see later on that when we rotate a magnet, it can produce an electric current. Also, electric motors involve the rotation of an electromagnet between the north and south poles of a permanent magnet. Okay, so we just covered a great deal about the theory of electromagnetism, and we'll stop now and have a little quiz on what we just learned.